and I have to kind of clarify it because I'm typically very sloppy with writing lower and upper indices, which you can also see here. So, for example, when we do this contraction, of course, for example, these two indices should be up, yeah. But for part of the community, at least where am I, normally you always write these guys as lower indices because it's implicit that you always contract them, yeah. So maybe some other people are more precise, but I typically always write the spinor indices as lower indices. But of course, being really correct, you should write epsilon AB as upper indices. Yeah, does it make sense? Yeah, so you will always see from me only lower indices, but if there is a repeated index, it's contracted over. Yeah. Okay. So we ended with the definition of the spinor-helicity variables and the momentum conservation. So now let's start to look also at helicities. Yeah. So as I said several times, we are in 4 dimensions. This spinor-helicity business only works in 4 dimensions. There is some extension of it in 6 and 3 dimensions as well, but kind of, yeah, the real spinor-helicity is in 4 dimensions. In general dimension D, as I said before, we are just stuck with usual momenta, and yeah, these advances don't apply there. So let's now look at helicities and the polarization vectors in 4D. Because we've already succeeded in getting rid of the 4 momentum, but if we would like to calculate amplitudes of particles with spin, we have to do something with polarization vectors, which also show up in amplitudes with spin, and they describe the spin structure. Okay, so as you know, in 4 dimensions, for massless particles, the spin degrees of freedom are given by helicities, and we have only 2. So we typically always, as you see in this Park-Taylor formula, denote them as plus and minus. Yeah, +1, -1. Yeah, and or if it was spin 2, +2, -2, just two values plus minus. Yeah, not everything is just spin 1. Yeah, we can also talk about gravitons, not just gluons. Yeah, so we have only 2 helicities. And you will see that they nicely play with these spinor-helicity variables. Now, so if we want to describe the particles with spin, in addition to for particle 1, to the momentum P1, we would also have to associate the polarization vector for each particle. And for massless, because we are talking about massless particles, we have 2 helicities plus minus. We can, it's a 4 vector again. We can, for example, choose the epsilon. So this is something you can, of course, find in any QFT textbook, for example, in this way. Yeah. So that's one choice of the plus minus helicities for the polarization vector. But of course, we don't want to talk about the 4 vectors anymore. We got rid of p mu, replacing it by lambda lambda tilde, and we would like to also rewrite the polarization vector in terms of some spinors. Yeah, because then, in the end, any contraction of the Lorentz indices just boil down to the contraction of spinor indices. And yeah, the polarization vectors, of course, it has the usual Lorentz index. So now, so that's what we will do now. Which one let me just move. So we now write no, that's the wrong one. We now write the polarization vectors in terms of spinors. Okay, so this is the correct prescription. So the plus, for the plus helicity, the polarization vector is given by this way. We again use the Pauli matrices to rewrite the Lorentz index or trade the Lorentz index for the spinor indices. And then we have some A, right, the A and A dot spinor. And the structure is following. Okay, so let me explain this formula. So there is a lambda tilde spinor for the particle we are describing, for which there is this polarization vector. And then here there is some auxiliary spinor, eta. Okay, eta can be chosen arbitrarily. Yeah. This is just reflected in the fact that if we have polarization vector, the usual polarization vector, we can also always shift it proportional to its momentum, and we are describing the same state. Yeah. So there is this redundancy in the polarization vector, and also we have redundancy in writing the polarization vector using the spinor-helicity variables. Okay. Then if you calculate an amplitude, the dependence on this eta should drop. Yeah? So the polarization tensor vector depends on eta, because there is this arbitrariness, how we choose it. However, this should drop, or this does drop, when we calculate an amplitude. Yeah, because the amplitude also in the usual language of polarization vectors, we can always shift epsilon mu proportional to the momentum p mu. However, the individual Feynman diagrams, if you calculate Feynman diagrams, do depend on alpha, but the amplitude doesn't. Yeah? So this is just another way how to see manifestation of gauge invariance in the scattering amplitudes. Okay, so let's finish this. So this was for plus, and for minus, we we just kind of flip the lambda tilde, and instead of eta, we have lambda with the A index, and then we have some reference here. And also you see that we are dividing by an angle bracket of eta and lambda here, and here square bracket of eta tilde and lambda tilde here. So for example, in these formulas, if we rescale eta, the rescaling drops. Yeah, because it has 1 power of eta in numerator, 1 power of eta in denominator. Same thing here with eta tilde. Okay, but you can already see here that if we rescale lambda and lambda tilde, the polarization vector for both plus and minus, it's not invariant under the little group rescaling. Yeah, so the momentum was invariant, but the polarization vector is not invariant. Therefore, the amplitude is also not invariant. Yeah, it's only the momentum. Okay, so we write these eta tilde are auxiliary spinors, which should drop. Sorry. Yeah. Yeah, so for the case of gravitons, you have to choose like plus, plus, minus, minus, and yeah, you can basically do it twice. Yeah, you do it twice. Okay, very good. Yeah, so now let's just look at this little group scaling. So we already said that under the transformation, when lambda goes to, what did I do, T lambda? I hope I did this one. And lambda tilde goes to 1 over T lambda tilde for a particular particle. Yeah, so for lambda 1, you do this scaling lambda 1 tilde. Then the momentum is invariant, but the polarization vectors are not. And how do they scale? So the epsilon plus under descaling, you see that you rescale lambda, as t lambda and lambda tilde as 1 over t lambda tilde. So this scales like 1 over t square epsilon plus. And for epsilon minus, again doing rescaling, lambda goes to t lambda, lambda tilde goes to 1 over t lambda tilde. So this scales like t square epsilon minus. Okay, and because there was already a question here on the gravitons, we can generalize this thing for any spin. And for general, spin S, this would just go as 1 over t to the 2s epsilon plus, and this would go like 1 t to the 2s epsilon minus, when S is the spin. So you see that for scalars, well, there is no polarization vector, tensor, spin, or anything for scalar. You see that S is 0, so 1 goes to 1. Yeah, but for spin 1, spin 2, we have all this dependence on t. Okay. Now let's start. So this is for a one particular, like external leg. Yeah, for one particle. So now we can apply this logic to the amplitude. Yeah. So now let's talk about an on-shell amplitude. And kind of one very useful thing to do when we talk about scattering amplitudes is to fix the external helicities. So maybe I didn't say it explicitly, you already saw it in this Park-Taylor formula that the particles there had fixed helicities. Yeah? If you do the Feynman diagram calculation, the helicity is just hidden in the epsilon tensor. Yeah? So you can just do the calculation and you can choose which helicity you want in the end, because the formula has all helicities at once, which is great. So you have everything at once. The bad thing is that you get like gigantic, horrible formula with many terms. But what happens to be true, and this Park-Taylor formula is a first manifestation of that, for a particular fixed helicity, you get simple expression. And when you work with the spinor-helicity variables, it's very useful and even necessary to fix the helicities in the first place before you even start to do calculations. Say, what are the helicities of external particles? Yeah. So yeah. So yeah, just to stressing this, that we have fixed helicities. So then, if we have some amplitude which has particles 1, 2, 3 up to n with some helicities plus minus for all of them. So it's either plus or minus. It's not plus minus, but you just fix what are the helicities for individual particles. Then from this analysis of the little groups and the polarization vectors, we know how the actual amplitude scales. Yeah? Because how does the particle 1 enter the formula for the amplitude? Well, it enters that through the dependence on momentum P1, let's say for particle 1, but P1 is invariant under little group. So the only other way how it enters, it's through polarization vector, epsilon 1. But we know exactly how the polarization vector scales now. Yeah? So the non-invariance under the little group scaling is only comes from the non-invariance of the little group scaling of the polarization vector. Okay, so if I have this amplitude and it has a particle I, which is a negative helicity, then under the little group scaling, it scales like t square. And if some particle j has plus helicity, it scales like 1 over t square. Again, this just comes from the polarization vector, because amplitude has a trivial dependence on polarization vector. It's just linear in it. It might have very complicated dependence on the momentum, but momentum is invariant. It doesn't contribute to this scaling. Okay, so now we are basically ready not to really derive, but verify that the Park-Taylor formula is the correct formula for a particular gluonic amplitude. So, so let me just remind you, and the Park-Taylor formula was for the 6 gluon amplitude, 1 minus, 2 minus, 3 plus, 4 plus, 5 plus, 6 plus. Of course, there is an extension to endpoint, which is kind of straightforward once you see the 6 point. And gluons are massless spin 1 particles. So S is 1. So this is exactly what we are talking about here. And the formula took this form, 1, 2 cube over 2, 3, 3, 4, 4, 5, 5, 6, 6, 1. Now you can already see there was something, apart from being extremely simple, there was already something super special about this formula because it only depends on the lambda spinors, not lambda tilde. Yeah, this is not true for a general amplitude. For other helicities, that will depend on both lambda and lambda tilde. The helicity when only 2 of the helicities are negative and the rest are positive, called them HV. We will get back to it a little bit later. These are very special. It only depends on the lambda spinor. And now, but I wanted to demonstrate here the scaling under the little group. So the particle 1 was negative. So if we rescale lambda going to T lambda and lambda tilde going to 1 over T lambda tilde, but lambda tilde doesn't show up, so we can forget it, just rescale lambda. Then you can see that rescaling lambda 1 going to T lambda 1, you get 3 powers of lambda 1 from the numerator, and there is 1 power of lambda 1 in the denominator. So indeed, it exactly scales like T square. The same thing is true for the particle 2. For particle 3, which is positive, has plus helicity, same as the other, you can see that if I scale lambda 3 going to T lambda 3, the lambda 3 only shows up in the denominator in 2 of the brackets. So indeed, it scales like 1 over T square. Okay, so this is just checking that the Park-Taylor formula has the right scaling under the little group weights, as it should from the helicities. Yeah, it's not deriving the formula. Yeah, here we are just checking that it all makes sense. Any questions here? Yes. Yeah. Yeah. For real momenta. Yeah. Yeah, well, they have 2 degrees of freedom, right, here inside as well. Yeah. So the way how it enters the lambda and lambda tilde here, despite they are complex conjugate, but they are complex conjugate. They are not the same. Yeah. It's not lambda equals lambda tilde. Yeah. So the degrees of freedom here are, yeah, the way how they enter the degrees of freedom. So yeah, lambda tilde is a complex conjugate of lambda, but it shows up as complex conjugate, not the lambda itself. So it's a conjugate of that, yeah. So from that you get, well, also there is one thing, of course, because of the complex conjugate of lambda lambda tilde, if you take this amplitude, and you can also flip pluses and minuses, for example. This is called a parity transformation. The only thing that you get is flipping angle and square brackets. Yeah, so it's a complex conjugate from that point of view. One is a complex conjugate of the other. Yeah. Now these, okay, yeah, that's it. Yeah, these formulas also make sense if you don't impose the reality condition that the momentum is real. Then they are independent. Yeah, but indeed, yeah, for the reality condition when the momentum is real, you think about them conjugate, but you have to conjugate. Yeah, they are not the same. Yeah, they are conjugate of each other. Okay, excellent. So let's just. I also want to show a small example of this general thing. So we said that for the general spin S, if you rescale epsilon plus, you get 1 over t to the 2s, and if you rescale epsilon minus, you get this t to the 2s. Now I can, for example, there is some fun thing you can do. I can give you some formula for a 4-point amplitude, and I say, this is a 4-point amplitude. And just from the scaling, you can figure out what are the spins of the particles incoming because of this scaling. Yeah. So let's just look at a simple example. Okay, so let's say this is some 4-point amplitude, very simple. And now the question is, what are the spins of particles 1, 2, 3, and 4? So, or helicities, not just spins. We can even say what are the helicities. Is it plus or minus? Yeah. So for particle 1, you can see that it shows up only through lambda 1. So there is lambda 1 cube in the numerator and lambda 1 in the denominator. So it scales like lambda 1 square. So we can immediately see that the helicity is equal to -1 of the particle. Yeah, it's like in the Park-Taylor factor, yeah, of particles 1 and 2. So the particle is minus and with spin 1. So the helicity is -1. For particle 2, we have lambda 2 cube in the numerator. So this must be also a negative helicity particle with spin 3/2, right? So the helicity of particle 2 is -3/2. So it's a particle with spin 3/2 and helicity minus. If you look at particle 3, this is a little bit more complicated. So you have lambda tilde 3 in the numerator and lambda 3 in the denominator. So if you rescale them, it's 1 over lambda 3 square, yeah, or 1 over t3 square. So this is a particle with spin +1, or helicity +1. And particle 4 has only lambda tilde 4 in the numerator. So under rescaling, it will rescale like 1 over t. So this means that the particle must have helicity +1/2. Okay, so I'm not saying that this is a meaningful amplitude. You can get it in any theory, but if you could, then this will be the helicities of particle of this amplitude, just from this little group scaling to figure out. Yeah. Okay, any questions here? Does that make sense? Okay, excellent. So now we start to do a little bit more diligent work and try to derive formulas for some simple amplitudes and kind of do the setup for doing the recursion relations that Shruti will continue in the afternoon at 3 level. Okay. No, wrong. Okay. So, so we now start with the simplest amplitudes that we can possibly have, and these are 3-point amplitudes. There will be a small caveat when we talk about the existence of 3-point amplitudes that we will see a little later, but they are the main building blocks for what happens next. Okay, so what is the setup? We have massless 3-point amplitudes. So now we talk about the conditions on external momenta, because we know that the particles are massless, so the p1 square, p2 square, and p3 square are 0 on shell, of course, also. We always have everything on shell. And we have also momentum conservation. Okay, as it turns out, this satisfies a lot of conditions, yeah? Because there is only 3 momenta, and we have all these conditions, because these are single conditions, but the momentum conservation is a vector condition for each component of P. So we would like to see what is the implication on lambda lambda tildes. How much are they restricted because of momentum conservation and on-shellness? So let's calculate p3 square. We know that it's 0. Yeah, we know that p3 square is m3 square and that is 0 because we have massless particles. But from the momentum conservation, P3 is minus P1 minus P2 as well, right? So we can just plug for that, and the minus 1 square is 1. So the thing that we really get is P1 plus P2 square. Okay. Now P1 plus P2 square, this is something that we wrote using spinor-helicity variables just last lecture. So remember, this was equal to the angle bracket 1, 2 and square bracket 1, 2. Yeah, using lambda and lambda tildes of particles 1 and 2. However, this is 0. Well, product of two things is 0 only if one of them is 0. So one of these guys must be 0. Yeah. Okay. Now we can also, to see the whole picture, we also do it for P2 square. This is equal to P1 plus P3 square. And this is now equal to 1, 3 angle and square brackets. And this is again 0. And the last one is P1 square, which is P2 plus P3 square. And this is square and angle bracket of 2, 3. And this is also 0. Okay, so too many things are 0 now. As it turns out, if you want to solve these three equations at the same time, you get two solutions. Yeah. Either all angle brackets are 0 or all square brackets are 0. Okay, so solutions. Well, there is always like a solutions when everything is 0, all angle and square brackets, but this is kind of a non-interesting overlapping solution. Then everything is 0, all momenta are 0, amplitudes are 0. Yeah, kind of too trivial case for us. But the interesting solutions are following. So either or angle brackets are 0. And what is the interpretation of that? Yeah. So the angle bracket, just to remind you, was an epsilon contraction. So let me here do it properly with the upper indices of two spinors, lambda 1 and lambda 2. So in order that to be 0, these spinors must be proportional to each other. Yeah, it's like vectors in 2 dimensions. Yeah, if the scalar product is 0, yeah, they are just pointing in the same direction. Yeah, so from this, lambda 2 as a spinor is proportional to lambda 1. Yeah, one is a multiple of the other one. It has only 2 components, so it's just a rescaling one of the other one. And because this is true for all of these brackets, the resolution is that all lambdas are proportional as spinors. Yeah. Now the other solution from kind of the symmetry you can see is that all lambda tildes are proportional because all the square brackets are 0. So this is okay. So for the 3-point on-shell kinematics, we are kind of forced to eliminate half of the variables because they are just all proportional. Yeah, not eliminate, but they are trivialized. Yeah, and the only real kind of information, the only non-trivial things that we can build is from the other set of variables which are not proportional. Okay, so what is the resolution of that? So arbitrary. Yeah, sorry, say it again. Yeah, so that's a caveat I will discuss just in a second. Excellent question. Yeah, if the momenta are real, kind of both of them are true. So we are in the uninteresting solution. However, for this particular case, it's useful to think about momenta as being complex. Yeah, so this is also the reason why there is no massless 3-point scattering in real life. Yeah, you don't have scattering of massless particles in real life. However, as kind of an imaginary object, which will be useful to build real objects later out of it, this is a useful thing to study. But you are absolutely right. Yeah, for the real momenta, we are on the overlap of both of them. Yeah. Okay, excellent, excellent. So let me continue with being quiet about what is real and not, or I can be explicit. Things are complex for me at the moment. Yeah. So for now, momenta are complex. because indeed, if we really insist at this step to have real momenta, then we have to stop and just say 3-point amplitudes don't exist. And that would be pity, because we can learn a lot from 3-point amplitudes. So now arbitrary 3-point amplitude, because of this condition, can be written in a following way. So it's either the product of all, it's either a product of angle brackets with some powers, unfixed at the moment. And this is the solution when all the lambda tildes are proportional. So we cannot, so if lambda tildes are proportional, we cannot use the square brackets, they are all 0, and we have to build everything from angle brackets. And similarly, the other solution is that we have the same thing with the square brackets. And this is for the case when all the angle brackets are 0 and all the lambdas are proportional. Okay? Any questions about that? Is that clear? We are basically left only with this. Yeah? And I haven't even specified what are the spins or anything. Yeah, just based on these general grounds of the 3-point kinematics. We didn't have any other option than to write one of these two amplitudes. Okay. So, because we know that the 3-point amplitudes are that simple, they are either the square brackets or angle brackets, and in addition, we know how the amplitudes should scale under the little group, we can directly write any 3-point amplitude for any spins, just from these two information. Yeah? Because first, it's obvious that if we, okay, well, let's just work it out. Yeah. So, so let's do a 3-point amplitude. So calculate or determine explicit 3-point amplitudes. So let's do a first example. So we do it for particles with spin 1. So if all the particles are of spin 1 in the problem, some of them can have positive and some of them can have negative helicity, then we can specify the helicities. So let's do one example when 1 is minus, 2 is minus, and 3 is plus. So I remind you, so I write it here again. We can have two solutions. One is only with the angle brackets, and the other one is only with the square brackets. And the thing that we would like to do now is to solve for these exponents. Okay, so it's this or the other one. So let's first do the first one. Yeah, we have two candidates, and we have to also solve for the exponents. What this amplitude can be. So now we do the little group rescaling. So we know that for the negative helicity amplitude, if we rescale lambda 1, we should get 2 plus 2. Yeah. So this means that for particle 1 minus, rescaling lambda 1 in this one gives me A1. Rescaling lambda 1 here gives me A3. So A1 plus A3 is 2. Now for particle 2, there's also minus helicity. So that shows up here and here. So A1 plus A2 is also 2. And now this is plus helicity. So rescaling lambdas, we should get minus 2. right? So for 3 plus, we get that A2 plus A3 is minus 2. Okay, 3 equations for 3 variables. We just solve them, and we get following solution. A1 is 3, A2 is minus 1, and A3 is minus 1. Okay, plugging here, the formula that we get is 1, 2 cube, 2, 3, 3, 1. Okay, so we get a 3-point amplitude for minus, minus, plus helicities, which has this form. Yeah, you see that this is kind of a short version of the Park-Taylor formula. It has the same numerator. It's just kind of just the contracted denominator. Instead of 6 particles, we have only 3 particles. Okay. Now, we can also attempt to use the second form. So this was for the solution when all the lambda tildes were proportional. How do we know that? Maybe all the lambdas are proportional. So let's just try the second general formula for 3-point amplitude and solve for the exponents. Yes? Not even that, yeah. We didn't say anything about tree level here in this particular case. You can always, yeah, no assumption. Of course, you can like take this amplitude and multiply it by a number. We cannot fix that number, yeah. Yeah, yeah. So here, this is tree level if you really calculate it, but there are no loop corrections. So this will be exact, yeah. Yeah, because well, yeah, that's one thing I wanted to mention. There is nothing there is no kinematical variable you can put inside the logarithm. Yeah, it's exactly because of these restricted kinematics that we had here. Yeah, because all the Sij's are 0, so you would have to put something in the argument of the logarithm. And this is a little bit detailed answer, but there is nothing for 3-point that you can put there which doesn't have a little group weight. And you have to put there something with little group, like neutral little group weight, like S over T or something like that. And nothing like that exists for 3-point, yeah, because the kinematics is so restrictive that all these objects are 0, all Sij's are 0. So there is nothing you can put inside the logarithm. So these are exact formulas. The thing that you can do is to just multiply it by a number, because that is not ruled out. Yeah, yeah. Yeah. 3-point amplitudes are completely constrained. Yeah, but by just Poincare symmetry. Well, we didn't say here anything about conformal. Yeah, but yeah, the 3-point amplitudes are completely constrained. Of course, that has a caveat because we said that 3-point amplitudes of massless particles are actually 0. Yeah. So, but the 3-point amplitudes are completely fixed from what we did here, only by little group weight. That was the first thing, and by specifying the helicities. We didn't use any other input from here. Yeah. It's just the lack of kinematics. Yeah, there is a lack of kinematical variables, so there is no richness in what type of functions you can build at 3-point. Yeah. Okay, and these are great questions. So let's finish the calculation here and look at the potential second solution, which had the other type of brackets. And see if we can just solve. Well, it's kind of obvious that we can solve for the exponents. So, so here, because we have the square brackets instead of angle brackets, it will have the same equations, but just with minus signs on the right-hand side. Yeah, because the lambda and lambda tilde scale oppositely with the sign. So let me just let me just do a little fast track. So the solution is the same as here with minus signs. Yeah. So the solution for this amplitude (1 minus 2 minus 3 plus) will be B1 is minus 3, B2 is plus 1, and B3 is plus 1. Okay, so what is the amplitude that we just constructed here? It has 2, 3, 1, 3 in the numerator and 1, 2 cube in the denominator. Yeah, note that here I sometimes write 1, 3 and 3, 1. The bracket is antisymmetric, so it just flips the sign. Yeah, this is not important for our discussion because, as I said, we are not fixing any overall thing in front anyway. Yeah, so so this amplitude has some problems. Do you see any problem with that amplitude? Naively? Well, one good thing to think about is, so we are talking about lambdas and lambda tildes, but you can kind of trace it back to what is the scaling in momentum. Yeah, so we know that P is lambda lambda tilde, and epsilon is something like lambda over lambda tilde or the other way around. It's kind of, if you think about lambda having a mass dimension, this is neutral, epsilon, while the P has like the double the mass dimension of lambda lambda tilde. Or you can think that lambda has a half and lambda tilde half of the mass dimension of the P. Okay, so here we had 3 brackets in the numerator and 2 brackets in the denominator. So it had positive mass dimension. Yeah, so it came at the level of Feynman diagrams from some vertex with a derivative. Yeah, and indeed, in the Young-Mills theory, this would come just from the vertex, 3-point vertex, which has AADA. Okay. However, this has 3 brackets in the denominator and 2 brackets in the numerator. So this comes from, if it went from some Lagrangian, it would came from something which is 1 over derivative. Yeah, so this is not a local quantum field theory. Yeah, so just from the mass dimension analysis, we can conclude that this is the right solution and this is not. Okay, despite just the discussion of the little groups allowed both of them. Yeah, but we want the amplitude to have positive mass. Well, for 3-point here, positive mass dimension. Then if you go to higher point, you know that you have also propagators. So that decreases the mass dimension from 1 over p squared. But for 3-point, there are no propagators. So everything at the level of Lagrangian must come from just a vertex. And that must have a positive power in momentum. Okay. Any questions here? Yeah, so yeah, this again, this would come from some local term, which is like a squared dA, where the derivative is responsible for the positive mass dimension. Okay, good. So here we concluded that for spin 1, amplitudes, know that I here didn't assume anything about what is the theory I'm calculating these amplitudes in. There was no input from the Lagrangian other than having that it must be a local quantum field theory. It must have the positive dimension. But I didn't say like it was a Young-Mills theory, it was some other theory and so on. The only thing that I assumed was helicity, 3-point kinematics. So this tells us that if we calculate that there is only one 3-point amplitude for a fixed helicity independent on the theory. Yeah, of course, it only exists in, this comes from one particular theory, but there is no other 3-point amplitude. It's not that I change the theory, I calculate the 3-point amplitude, I get something else. I cannot. Yeah, there is only one amplitude. And for 3-point, this is always true for massless particles. The 3-point massless amplitudes are completely fixed. The structure is completely fixed. The explicit expression is completely fixed. And you didn't have to make any assumption about what was the theory in which they lived. Yeah. So let's finish this discussion and just to see just to then say in which Lagrangians would generate these amplitudes, just from some very simple analysis. So we calculate this amplitude for minus, minus, plus helicities. We can also calculate this amplitude when you flip the minuses to pluses. And from what we already discussed, this is just given by the parity conjugation. Yeah, so the parity flips the lambdas and lambda tildes. You did see it in the explicit forms for the polarization tensors. When going from plus to minus, you just reverse the roles of lambdas and lambda tildes. So the same thing also happens, of course, at the level of amplitudes, because the momenta, they do not, they are symmetric in lambda lambda tilde, so it's only the polarization vectors which really make a difference. Okay, so these are the 3-point amplitudes of spin 1 particles. There are no other 3-point amplitudes. And these amplitudes are actually generated, so they come from Young-Mills Lagrangian. So they come from the F-square. So I think in the quantum field theory, you discussed the Young-Mills theory. This is F with covariant derivatives. So the F generates both the 3-point and 4-point vertex. For 3-point amplitudes only, this contributes. And when you put external momenta on shell and fix the helicities, you would get these amplitudes. Okay. Now you can also ask the question, why did I say that 2 of the helicities were minus and 1 was plus? I could also say that all of them are minus. Why not? Yeah, definitely can be. And so I can calculate amplitude minus, 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 again, without any assumption what is the theory, not using Lagrangian or anything. I'm just playing this game of having the product of angle brackets or square brackets and fixing the exponents. Now I have to fix the exponents such that the little group scaling for particles are for particles minus, minus, minus. Okay? And if I do it, I get that all exponents A1, A2, and A3 are 1. Yeah? It's just a solution, the system of 3 equations for 3 unknowns. And yeah, I just get 1, 2, 2, 3, 1, 3. Okay, so here, and I can get the same thing for 1 plus 2 plus 3 plus, you would just have the square bracket 1, 2, 2, 3, and 1, 3. Yeah, again, related by the parity. Now, you can ask, okay, so there is only one 3-point amplitude with these helicities. Where does it come from at the level of Lagrangian? If you are interested in that question, maybe you are not interested to ask that question, but if you are, you can do just some derivative counting. And here, the counting of derivatives was that for each bracket, you can think as one derivative. That was the thing that I did there with the counting of lambda lambda tildes, because P is lambda lambda tilde, and the bracket is lambda lambda, but this is because epsilon switches some lambda lambda tildes without changing the dimension. So this came from the theory with a single derivative, which is exactly what is inside the expansion of the F-square term. There is a term AADA. Now here we have 3 brackets, so we need 3 derivatives. So the thing that generates this 3-point amplitude would be Lagrangian F cube. Yeah, because the F cube will have 3 derivatives in it. Yeah, it would be basically dA cube. Yeah, that is the part of the Lagrangian that contributes. Which also means that if you are restricting yourselves to Young-Mills amplitudes, Young-Mills theory, these amplitudes are 0. Yeah, because you don't have such term. Okay. Okay, any questions here? So from this, you saw that there was nothing really special about spin 1, and we can do the same analysis for general spin. Okay, so we can do the same analysis for the general spin. So we have a 3-point amplitude, which has so it's an arbitrary 3-point amplitude, which has particle 1 with helicity h1, particle 2 with helicity h2, and particle 3 with helicity h3. What we do is to write this ansatz. It's either the product of angle brackets or product of square brackets. Now, we solve 3 equations for 3 variables for the helicities. So solve for A1, A2, A3. And separately, we can also do the solution B2, B1, B2, B3. And only one of them will be the one which is realized. And if the sum of A1, A2, and A3 is bigger than 0, this means that we have a positive dimension here. It's the solution number 1 with the values of A1, A2, A3 that we got. If not, smaller than 0, then it's the number 2. Yeah, because then by this conjugation, if this is positive mass dimension, this is negative, and the other way around. Yeah. So this gives us solution for any 3-point amplitude for any values of spin. Now you can realize some small caveat because we can calculate amplitudes with spin 50 if we want. Yeah. And probably you heard something like that there are no interacting quantum field theories with particles with spin bigger than 2. So something is a little funny here because 3-point amplitudes we can write for any spins with no problems. And that is indeed true. The 3-point amplitudes exist, but in order to build higher point amplitudes, this only works for special spins, and now we get all these restrictions. For example, we find that there is no spin 3 interacting. There is no spin 3 amplitude for bigger than 3-point. Yeah. So yeah, that I quickly review here. So let me again here emphasize the 3-point amplitudes are fixed. The one thing which is not fixed in front of these kinematical parts are the coupling constants. So if we are asking like the only thing that it fixes is the kinematical part. So there can be G in front, and the G, for example, can get corrections at loops or things like that. But it cannot change the kinematical part. Yeah, that's the statement here about the little groups and the scaling. Now, if we have special amplitudes for this general spin, when all particles have the same spin, so same spin. Yeah, because these formulas work for arbitrary spins, as we had these examples. You can take particle with spin 2, spin 4, spin 6, and so combine them together. It's always possible. But if they have the same spin, as we have, for example, this amplitude, but the spin is S, you will see that there is a nice solution that is basically taking the spin 1 and raising it to power of S. Yeah, so the graviton amplitude for spin 2 is just a square of the Young-Mills amplitude, which is the origin of color kinematics and things that Henrik will discuss later. But yeah, here it's kind of a trivial manifestation for these simplest 3-point amplitudes. Okay, very good. So I think we had a longer break, so I take like 10 more minutes now. And, yeah, question? spin-dependent phase. So the statement here is about kinematics. Yeah. So so the kinematical part is completely fixed. You can multiply it by whatever you want. This is not fixed. Yeah. So you can multiply it by g, which but depends on what. Yeah. There is nothing to depend on. Yeah. Yeah, great question. Yeah, we will get back to it. Yeah, we will get back to it. Yeah, exactly now, because as Lance pointed out, you have particles, okay, just for spin 1, you have particles 1 and 2, but the formula, so spin is 1, so this is not there, is antisymmetric in 1 and 2. Yeah, so in order to make the amplitude symmetric, you have to do something more. Yeah, so the kinematical part is fixed, but there is obviously some more degrees of freedom you have to add, which, as you know, for gluons would be color. Yeah, so in order to get a symmetric amplitude, you have to multiply it by FABC. Yeah, for that. But this will also enter now in the discussion of 4-point amplitudes, where I wanted to mention that. Yeah, but great. Yeah, thanks for pointing that. Yeah. No, we should, for real momenta, we just get 0. There are no, so the momenta, as I said, this disclaimer, are complex. Yeah, so we have to, so these are complex. If we really insist that the momenta are real, we are getting 0. No interesting 3-point amplitudes on shell. Yeah, so So, right. So note, my statement is about kinematics. Yeah. So if anything that you do at the level of Lagrangian might some effect on amplitude, it might only kick in the prefactor here, because you cannot do anything with the kinematics. Yeah. So in principle, this G can depend. Yeah. Can be renormalized, it can depend on some scales or something, or theta or something, but the kinematical part cannot. You cannot change that. Yeah, so there can, so that's the statement here. Okay, excellent. So, okay, I will shorten that, but let me now discuss the 4-point amplitudes. So we saw that we can write 3-point amplitudes for anything, but this was for any spin, but this will fail for 4-point. So before doing the proper 4-point amplitude, let's first consider the 4-point amplitude on a factorization channel. Yeah. So so the 4-point amplitude in general has poles. And this can be 1 over S, 1 over T, or 1 over U poles. Yeah, unlike the 3-point amplitude that doesn't have any poles, because ST and U, there is nothing like that. Yeah, we said that there are no non-zero kinematical invariants Sij. So, so on the pole, S, which standardly is P1 plus P2 square, is 0. And we know that P1 plus P2 square is also angle bracket 1, 2, square bracket 1, 2. Or also, by momentum conservation, now for 4-point, this can be also written as P3 plus P4 square. This is also 0. So now you can see the trickiness of the momentum conservation, because on one hand this is equal to that, on the other hand it's equal to that. Yeah. And you can see that unlike for general D dimension, for 4 dimensions, just sitting on S equals 0 on the S channel, you have 2 options. Yeah, there is no single S channel, but there are two different ones. Yeah, because you can either send this thing to 0, and as it turns out, at the same time you have sent this to 0, so that's one option. And the other option is that you send this bracket to 0, and this also forces sending this bracket to 0. Okay, so this is option 1. And this is option 2. Okay, and how to understand it? So this can be also understand from this 3-point kinematics, because if S is 0, the amplitude factorizes into a product of 3-point amplitudes, and they are completely fixed. Yeah, and they have be of one of these two forms. Well, they have a fixed form. So if we consider the 4-point amplitude 1 minus, 2 minus, 3 plus, 4 plus, then on the factorization channel, we get a 3-point amplitude 1, 2, and P, and then P, 3, and 4, when the internal momentum is now on shell. Okay. Now, the fact that the 4-point amplitude must factorize as a product of 3-point amplitudes, yeah, so here the factorization is into 1 minus 2 minus P plus times a 3 plus 4 plus P minus divided by S. Okay, where S is 0, so we are going near the pole. So this condition, so we said that there were no conditions on 3-point amplitudes, like which spins are allowed. Everything was allowed. But once we consider 4-point amplitudes with arbitrary spins, but with helicities, and we demand that the amplitude factorizes into a product of 3-point amplitudes, this puts a huge constraint now on everything. Yeah. So the consistency of the 4-point factorization puts a huge conditions, and it's also related to what Lance mentioned. So I think, yeah, I will not eat much more time. I will kind of skip my nice derivation and just give you the result. So consistent 4-point amplitude factorization. Tells us that if we have arbitrary 4-point amplitude of particles of some spin S, now it doesn't matter on particular helicities, but let's say that all particles are the same and are of spin S, then in order to factorize correctly on all channels, on S channel, T channel, and U channel, as a product of 3-point amplitudes in a local quantum field theory, so you don't have any higher pole channels. Yeah? So that's kind of the condition that enters in. All the poles of the amplitude are 1 over S, 1 over T, or 1 over U. You cannot get 1 over S square. 1 over S square pole is not generated by any Lagrangian local. Yeah? With the canonical kinetic term. Yeah, okay, local Lagrangian with higher derivative terms. So only poles are 1 over S, 1 over T, and 1 over U. You impose that. You impose that on each pole, it factorizes as a product of 3-point amplitudes. And then, taking these conditions together, you only get 3 options for which 4-point amplitudes are allowed of which spins. You get as one option which will be scalar theory, S equals 0. Okay? In that case, the 4-point amplitude, it's really simple. The 3-point amplitudes are 1, and the 4-point amplitude is 1 over S plus 1 over T plus 1 over U. Okay? And obviously, it correctly factorizes on all poles. The other option would be scalar, spin 2. This will be graviton. And the 4-point amplitude, A4, will take some special form. It will have some angle and square brackets to certain power, to the 4, divided by STU. Okay, that's the second option for the 4-point amplitude. And that's it if we don't say anything else. Now, there is also a solution for spin 1 amplitude, but in order to do that, we have to introduce color. We cannot have single gluons interacting. Yeah? There is no theory of a single interacting gluon. Its 4-point amplitude doesn't factorize correctly, doesn't satisfy these 2 conditions. Okay? But if you introduce color, you dress the amplitude with some structure constants, which are antisymmetric, then you get consistent factorization. So the last solution is spin 1. Okay, I say gluon. Spin 1. But for that, you have to add color. And then the 3-point net, then we have to modify what we meant by 3-point amplitude in the beginning for spin 1. So when we wrote this formula for spin 1, as was pointed out, this is now antisymmetric in 1 and 2 in the first place. So, but in order to get consistent factorization, we have to make it symmetric, so we have to multiply it by F, A1, A2, A3. And this, if you take this as the 3-point amplitude, then it factorizes correctly. Its 4-point amplitude factorizes correctly. And we know that indeed, in Yang-Mills theory, we have some SU and gauge group, and this introduces the constant. Okay, so this was just saying that 3-point amplitudes exist for any spins. If you then go to 4-point amplitudes, and even without calculating 4-point, we haven't calculated any 4-point amplitudes, but we say that the 4-point amplitude would be 4-point amplitude factorizes into 3-point amplitudes and has single poles, then we are already getting huge reduction of what is possible. And here I only discussed things where all 4 particles had the same spin. You can derive also much more complicated conditions when you have combined, something is spin 1, something is spin 2, and so on. But if you restrict yourselves to only same spin, you are killing everything starting from spin 3 and up. And you are only left with these 3 options for spin 0, 1, and 2. And spin 1, you are even forced to have color, to have some extra degrees of freedom here. Okay, questions?
Just a quick question here. At the 4-point, that means you also add all permutation of the external legs, right?
Yeah, so this is saying here the condition is that on all 3 channels, ST and U, it factorizes.
Okay.
Yeah, but in different amplitudes, right? Because here I showed the S channel, but you have also T channel and U channel, which is different 3-point amplitude.
I mean, the final result is sum of all of them, all these permutations.
What do you mean? This?
Yes.
This is a 3-point. Yeah, this is going back to 3-point.
The
4-point gluon amplitude would have all the permutations. Yeah.
What about the graviton?
No, this is the full graviton amplitude.
Okay.
It has ST and U.
Sure.
Yeah, so it has all 3 channels. Yeah, this is the full amplitude. It's remarkably simple, but that's, yeah. Yeah.
So this seems more like a tree-level statement now. Is that correct?
Right. So this is factorization of 3-level amplitudes now. Yeah.
Okay.
This is a 3-level statement.
What about half-integer spins? Is that consistent here?
Yes. So it is possible. Yeah. You can add a half-integer spin. Of course, you don't have the interacting like free spins. You have to add something else also apart from just. So then you are in the world of like combining different spins, and yeah, you can definitely include them. Yeah. You just don't have like 3-point fermionic amplitude. Yeah. Fundamental. Yeah. You have to exchange something else. But yeah, you can definitely include them. Okay, yeah.
So you can take the 4-point factorization, and that can factor into 3-point, but the 3-point factorization is going to be dealing then with the complex momenta.
Yeah, yeah. So okay, so that's a great question. Now the 4-point amplitude. Okay, so let's now talk about real complex. The 4-point amplitude exists now for real momenta. We know that we have 4-point scattering in the world. Yeah. Now on the factorization channel, it factorizes into 3-point. Now the 3-point only exists for complex, which also means that the kinematics that puts you on the factorization channel, it's a complex kinematics. Yeah. Because it only exists for the complex momenta.
How can we see that checking factorization at 4-point ensures that we'll have also consistent factorization at higher points?
It doesn't. So in principle, you have to check also higher points. Yeah, yeah, it's a very good question. So these are only theories which pass the 4-point check. Okay, they will pass the any point check then later, but it's not guaranteed. And here, the result is clear. But once you start to do a more complicated game with including many other spins, yeah, so interacting spin 0, 1/2, 3/2, 2, then indeed it is not enough just to check 4-point, and there can be certain amplitudes which pass the 4-point check. But then if you kind of go, let's say there is a 4-point amplitude and it looks perfectly fine, yeah, because it factorizes into 3-point. But now if you consider 5-point amplitude factorizing into that amplitude, you find inconsistency. That can happen. Yeah. So in principle, the 4-point is not enough to check.
So
yeah.
How do we ever say that we have a consistent QFT by? Yeah, it should factorize at all points, right? So that seems like a difficult thing. Like you have to check at each order. Probably there's.
Yeah. But then you have to then consider like interactions, like many point interactions with like new interactions. Yeah. So yeah, in principle, if your task is to classify all possible amplitudes which factorize on all channels, yeah, in principle it's unbounded problem for any spin. But in practice it will be a bounded problem. Yeah, in practice you will be able to prove that for certain things it terminates at certain number of points and so on. Now what I wanted to show here is just that if you take the same spin, yeah, you already get like the right menu after imposing the 4-point factorization. You don't get any other constraints. You are not killing the scalar theory, or you are not killing the gravity, the Einstein gravity linearized. Yeah, but actually this work with classifying the other interactions was done relatively recently, a few years ago, and there was a complete classification and of everything, all interactions which correspond to consistent factorizations. Yeah.
Okay, thanks.
Yeah, here is a question.
So when you consider complex momenta for 3-point amplitude, but 4-point amplitude, if you want to have real scattering amplitude, then you might only like choose real.
Yeah, so the statement here is 3-point is complex, 4-point is generic, so real. However, 4-point factorization still happens for the complex momenta because it factorizes into 3-point, and that these are complex. Yeah, but the 4-point amplitude, not on a factorization channel, just 4-point amplitude without sitting on anything special, that exists for generic real momenta.
Yeah, so we always can choose real part for 4-point.
You can always choose, at 4-point, you can always choose real momenta. Yeah, there is no abstraction. Only at 3-point there is an abstraction because you don't have enough real degrees of freedom to satisfy all conditions. You need just complex degrees of freedom at that point.
And for the solutions for 3-point amplitude, is that why is only 2 types of solution?
Sorry, the 3-point, if it applies to 4-point, or?
No, only when we consider 3 points.
So this is, these solutions is just kinematics. So in 4 dimensions, if you have 4-dimensional theory, if you take an amplitude, specify the external helicities, the form of the amplitude is completely fixed. You don't have to say what was the theory you calculated in or anything. There is only one 3-point amplitude for fixed external helicities, up to a coupling constant. Yeah, the kinematical part is completely fixed, just by that.
So the solution is from the kinematics that, like, external momenta is massless and momentum conservation.
The external momenta are on shell, satisfy momentum conservation, and must be complex in order to get non-zero solution.
Yeah, but we can have like the what is the name of bracket?
This is angle brackets.
Angle bracket equals to square bracket.
No, it's not quite equal. Yeah, the complex conjugate of that for real momenta. Yeah.
So you consider complex momenta.
We consider complex, so we are not imposing that constraint.
Yeah, so we can have like angle bracket 1, 2 equals to square bracket 1, 3.
If we do that, if we consider real momenta, we impose that condition, we get the 3-point amplitude is 0. We get no solution. Well, the only solution is that all momenta are 0. Yeah, you have to keep everything complex and don't impose that condition for 3-point amplitudes to exist.
I mean, so you can have that solution, that kind of solution, not the constraint.
Yeah, I think this is. Yeah, okay, we can chat about it later. So
last question, we are already.
I think we are quite over time. Maybe we can just leave it to a break, and yeah, you can please come to me and yeah, thank you.